Welcome, everybody. Hi, I'm Katie Cassetta. I'm the Associate Director of the Ideas Festival. So glad to see such a great turnout for this session. I'm being instructed to move over. Hi. We wanted to put together a series of presentations about innovations in the climate and conservation space that seem like something you might see in Dune or Star Wars, but that's actually within grasp or even here today. Some of these technologies, like geoengineering, which is the manipulation of our weather, are more controversial than others, but we'll get into that. So this session is a little different. Rather than a panel, we'll have 3 talks in a row. We won't have a regular Q&A, so please stick around after the session ends if you'd like to ask our speakers a question. So we'll start with Harry Atwater. He's an applied physics and material science professor at the California Institute of Technology. He'll address a couple different projects, among them the space-based solar power project, which is aiming to collect sunlight from space, transform it into electricity, then wirelessly transmit that electricity wherever it's needed, including to places on Earth that currently have no access to power. Pretty cool. Then Julia Marsh, co-founder and CEO of Sway, who's using seaweed as an alternative to single-use plastic packaging. And I wanted to tell you guys that Julia first presented the seaweed idea as a PhD student here at the festival in 2019. And she's come back all these years later to share an incredible progress report with us. And she has samples of the product that you'll be able to touch and feel, which is just so excited that it's pretty much coming to market. And she'll share more with us about that. And finally, Kelly Wanser, who is the executive director of Silver Lining. She advises on a groundbreaking project looking at marine cloud brightening, a form of geoengineering that could reflect the sun so that temperatures here on the Earth's surface stay cooler. So thank you so much to the 3 of you for joining us, and we'll begin with Harry Atwater.
Good afternoon. So I'd like to tell you a story that began about 10 years ago at Caltech, which aimed to look at the science advances and technology developments that would be required to enable a scalable, large-scale technology for space solar power. So we'll get started with this story. But our story begins on Earth because the story of solar energy on Earth is truly a remarkable one. When I was a graduate student, the entire world had 1 megawatts worth of solar. That's less than we now deploy on the Caltech campus. And since that time, the growth of the solar power capacity of the world has grown 1 million-fold. Truly a Moore's law increase in the capacity for solar energy. During that time, the cost came down by a factor of 500. And today, the cost of a solar panel on your roof is less than the cost of a window in your house. So this tells what a transformation this has been. However, solar energy is wonderful, but it has a few limitations that have to do with variability. There's daily variability. It's very predictable, day and night. We rely on it as humans. We're happy to have nighttime so we can go to sleep. But if we wanted to generate as much power as possible, we would like to be in a place where sunlight was available 24 hours a day. Not only daily variability is a challenge, there's also seasonal variability. You could imagine using batteries that also transformed in the last decade to handle the daily variability. But we need to be able to store power in some places. And for example, this curve here on the right of my slide here shows seasonal variability in Gothenburg in Sweden, where the sunlight available in the winter is a factor of 10 less than in the summer. So you need to be able to store power or have power be available throughout the entire year. And with solar energy without storage, that's a real challenge. So one concept to address this is space-based solar power. And if you run the numbers, it turns out that there is 9 times more energy available than on Earth in space on a daily basis, on a diurnal cycle basis. First of all, there's 30% more power in space to begin with because the atmosphere filters some of the solar power. Plus, that diurnal variability, the day-night cycle and weather, creates another factor that in total means that if you could have a satellite face toward the sun where it's always noon, 24 hours a day, you would have 9 times more power. So it's available all the time, every day of the year, unaffected by seasons, weather, or location. Moreover, the scheme that we have developed for space-based solar power enables wireless beaming of power. And wireless beaming of power means that we can beam power to any location on Earth, including locations that don't already have a utility grid. For example, in developing parts of the world, did they build a copper landline network for telephones? No, they went directly to mobile phones, wireless phones. So you could think about now developing a similar concept for wireless power transmission and bypass the whole development of a utility grid. And using the technology that I'll tell you about today, we've been able to do an analysis that suggests the cost of power could be about 7 to 70 cents a kilowatt hour. So what does that number mean to you? 7 cents a kilowatt hour is less than the power rate that you pay as a ratepayer in your monthly utility bill. 70 cents is a little higher in most places. But for example, the price of power in Europe is often higher than this, and particularly during the time last winter in Europe when Russia halted gas supplies to Europe, the price of power went well above this level, and they would have been grateful to have space-based solar power. So this is a really audacious idea, and like any audacious idea, you have to think about what are the challenges. So one challenge is, could we actually build a large-scale solar power station in space? And how would you do it? How would you go from the small scale all the way to the large scale? How could you show that it would be safe? Would it be durable enough to last a long time? So you have to get a return on investment if you're an investor. Could the power be price competitive with conventional electricity? And our simple analysis that I just showed you suggests that it could be. But we also have other questions. Can we prove that it can't be used as a space weapon? That's one question I often get. And I'll address that right now. And I can tell you confidently, by laws of physics, I'm happy to explain to you afterwards, that we can build a system we can guarantee won't be usable as a weapon. So, and the power densities will be safe in the transmission. So space-based solar power first entered the public discourse in this prestigious journal, a science fiction story by Isaac Asimov in 1941, which is a notable date because that predates the existence of the space program or any spacecraft or even the invention of the solar cell. So some people have the capacity to really see far into the future, and Asimov was such a person. And since Asimov's fantastic prediction, there was quite a bit of development. In 1968, the first patents on such a system were developed. And throughout the 70s and 80s and 90s, there was the development of concepts for large-scale systems that would build in space, kilometer-scale structures that would require a lot of in-space assembly. And the conclusion always came down to the idea that this was a wondrous idea, but it was always way too expensive to be practical. And so indeed, the specific power, the power delivered per mass of kilogram turns out to be very important. It's expensive to, although space launch is getting cheaper, it's still more expensive than building things on the ground. So after 55 years, why hasn't this been done yet? It's because of cost and mass. So if you're a technologist or a physicist, you want to think about how do I dramatically, in a transformative way, reduce the cost and the mass? And that's the approach that we have taken at Caltech. These are my team of collaborators, Sergio Pellegrino and Ali Hajimiri. And together, what we have developed is what we like to call a component-led revolution. Just like the components made possible things like the iPhone or the computer, it wasn't the whole system design. The components are the things that need to be revolutionized for space solar power. So instead of using rigid solar panels like you would put on your house, we make flexible solar panels that are thinner than the Aspen Ideas tag that each of you is wearing, about half as thick as that. These are flexible cells. And in fact, our group developed technology that set world records for photovoltaic conversion efficiency using this kind of thin cell. Thin cells are, the physics shows, are even more efficient. We changed the RF power generation from heavy magnetrons like in your microwave oven to small silicon-based chips like in your iPhone. And the structures in space, instead of being rigid, heavy structures, have to be built in space. they can be unfoiled and uncoiled like an umbrella. And so this is the idea, to build a modular structure consisting of tiles, the basic unit of power harvesting and power transmission, that are inserted into strips that go into modules and build a system. And the overall, if you think about harvesting solar power on the ground versus harvesting it from space, the idea is to use a receiving station that's very much like the one you'd use on Earth for a space-based, for a utility solar installation, but now to just use an array of microwave antennas that receives the power from space. So in fact, the very same installation in Colorado or Arizona or California, sort of few hundred meter square area, could produce solar power in the daytime from Earth and space solar power 24 hours a day. And so this is what we imagine it would look like, a space power station based on this modular concept. And I'll show you a little bit about the development of these structures. This is a structure here that shows the, so you can go ahead and advance it now, right to about there. This structure is the lightweight structure. These are made of all carbon fiber materials. And this is a meter square scale demonstration of the structure that then deploys out like an umbrella in space. And in fact, I'll show you in a minute that we did this in space. We built RF antennas also out of materials on plastic sheets that are thinner than your conference badges. And all the power generation, as I mentioned, is with RS CMOS circuits, which have sort of milligram scale mass. So this is, and we developed a way to make solar cells the same way solar cells, I showed this millionfold growth in solar power and 500-fold reduction in cost. How was that done? It was done using very simple, cheap processing of silicon. In space, we use gallium arsenide as a solar cell material, so we developed a way to make gallium arsenide solar cells instead of the expensive way they're made now, by the same way that solar cells are made from silicon. So that enables you to use the same manufacturing equipment and to enable cells for space power to be 100 times less expensive than today. So we had a chance to test this out. And in fact, we had a first project launch, the Space Solar Power Demonstration Project, that launched on January 3rd, 2023. There's our SpaceX rocket being launched from Cape Canaveral with 3 payloads, Maple, Dolce, and Alba, which tested the microwave power, space structure deployment, and the solar cell operation. So I'll tell you a little bit about Alba, the solar power project. This is Alba being built in the lab. It's undergoing testing in the lab. There it's being launched into space. This is the spacecraft deploying from the SpaceX rocket. This is a view of Alba in space. And then so we launched the spacecraft into a polar orbit, and that means that we have day-night cycles. So about every 90 minutes in low Earth orbit, we go through a day-night cycle. And so this heat map shows the color map here shows the current density and the temperature of each cell as it goes through its polar orbit. And we collected massive amounts of data on a bunch of cells that had been made only the month before in the lab at Caltech. So normally, solar cells take 5 to 10 years of validation to go from the lab to being qualified in orbit. And so this went in a month's time. One of the pièces de résistance of this project was to beam power. And the Maple project enabled us to use those flexible antennas to beam power, first from one part of the spacecraft to another, and then from the spacecraft out this tiny little circular window you see on the left-hand side of the slide, out to the Earth. And standing on the top of the electrical engineering building at Caltech in Pasadena, California, in April of 2023 was this team with my colleague Ali Hajimiri, and they set up their antennas, and right at the time, around midnight, that the spacecraft in its polar orbit went over Southern California, they saw a little blip in the power being generated by their antenna against the background. And that was the first example of space solar power being beamed to Earth using the scalable technology that will be able to make this scale one day. So for any audacious technology, you have to ask, is it preposterous? Does it violate laws of physics? Does it go faster than the speed of light? Does it involve negative energy? No. Is it plausible? Is it possible? And if you pass those hurdles, is it preferable? And is it predictable? So we've been able to show that it's not preposterous. We've shown that it's plausible and it's possible. And the next steps will be to show that it's preferable and predictable and scalable. And we can build a sustainable source of solar power for the Earth. Thanks.
Wow, awesome. Hello, everyone. How epic was that? So cool. Such a pleasure to be here. I'm Julia Marsh, and I'm here to share with you a little bit of a personal story first, as soon as my slides appear, and there they are, I think. Yes? Okay, I'm here to ask the question of what if? And that slide should be appearing here, and the notes should be appearing here. And the notes aren't quite yet there. So I'll keep going. There we go. So I loved Harry's story because it perfectly teed up what I was about to share with you all. The future often feels very far away, and we oftentimes don't realize that we're sitting inside of an inconceivable future that was dreamt up just a few years ago. And I know that because 5 years ago today, I was standing on stage sharing what I thought might be an inconceivable future with you all at Aspen Ideas. I was invited by my dear friend, mentor, design icon, Brian Collins, and his photo should be appearing on this slide, but it is not quite there. There he is, wonderful man. And we talked about the plastic problem and how it is a problem so gargantuan that it affects all life on Earth. And there's no singular, clear solution for it. And we talked about what if design and nature could help us create a solution that could rectify plastic at scale. And then I got the opportunity to share a seemingly inconceivable future, the idea for a materials company that would utilize seaweed to replace plastic. And we would do so in a way that didn't just replace plastic, but actually regenerated ocean health, replenished soils, and we would do it using a technology which at the time did not exist. And at the time, I felt so vulnerable sharing this idea with the Aspen community because I didn't know if I sounded insane or not, and how you would receive this idea. It sounded like sci-fi. But then you swarmed the stage afterwards, and you told me how this idea really resonated with your vision of the future. And that enthusiasm gave me the courage to start this company. So most talks end with a thank you, but this one starts with a one. Thank you so much for giving me that courage. A lot. Thank you. A lot can happen in 5 years. A lot of change can happen. I mean, just 5 years ago, Impossible Meat, Beyond Burger, they were seen as a novelty, but now you can get them in Burger King and Costco. EV charging stations were few and far between. Now 95% of the US population has access to charging stations. Pickleball was not being talked about. And now it's here on campus. And 5 years ago, clean materials, regenerative materials, bio-based feedstocks, they were seen as still a niche that was kind of cordoned off as an afterthought. And that has changed in the past 5 years. I am in very good company as an enthusiast for bio-based materials. I'll show you some examples. Ponda is using wetland regenerating cattail fluff to replace synthetic down. MycoWorks here in the United States is using mycelium to replace leather. Woola over in Estonia is using waste wool to replace bubble wrap. Over in Germany, they're using coffee grounds at Kaffee Farm to replace reusable cups. Shellworks is using microbes to replace durable, rigid containers. Down in Australia, Great Wrap is using waste potato peels from the chip industry to replace cling film. Over in the UK, they're using pea protein to replace soluble films that are used in detergent pods. And in California, where we're from, Gaia Star is using clay to 3D print replacements for single-use cups. So cool. Seaweed, coffee grounds, coconut husks, shrimp shells, microbes, pea protein, ag waste, grasses, microalgae, bamboo, and more present many viable pathways towards a cleaner, more biologically circular future. And there's not going to be a silver bullet, but that's okay because nature is diverse and the solutions should be diverse too. And rather than degrading our planet, these materials have the potential to actually replenish the planet along the way. They're not a science project, they're here. So all we gotta do is scale them. Everybody here knows that the challenge ahead is scale. For example, for the sake of focus in this talk, I'll talk about the 5 trillion bags, wrappers, and pouches that are used and produced every single year. That's 160,000 bags per second. 99% of these bags are produced using petroleum, and after they're used, only about 1 to 3% of them are recycled, which means that the vast majority ends up in landfill or in nature or in our communities or in our own bodies. Now, there's an argument to be made that we could probably just eliminate a lot of that material, and I think we should. There's a lot of reusable solutions out there, but what about the necessary materials? Well, this is the opportunity for us to take advantage of the infrastructure that already exists around plastic. Our theory is that to truly shift away from extractive systems, we need to optimize for this scale. So rather than sourcing from a polluting resource and designing materials that last forever, what if instead we worked with a generous resource like seaweed and engineered those materials to decompose naturally? And then we would complete the loop of biological circularity just as nature intended. Well, that leads me to the company that we started, that you helped us build. Sway, a materials company based out of California using seaweed to replace plastic at scale. And I'll share that those 5 years have not been easy. It's really, really hard to beat plastic, primarily because plastic is an amazing material. I'll share a slide from my presentation 5 years ago because it remains true. Plastic is fantastic, okay? To beat plastic, you gotta be thermally processable, lightweight, machine compatible, moisture resistant, heat resistant, printable, durable, stretchable, translucent, shelf stable, food contact safe, and you gotta be cheap. So that's no small order. We figured out that within the plastic industry, the world revolves around pellets. If you want to beat plastic, you got to design a pellet that can go and flow wherever plastic is manufactured. The problem is, we discovered, seaweed doesn't melt. It burns. And so it took us about 3.5 years with a team of scientists and engineers that we assembled, going through hundreds of formulations to figure out a way to make seaweed melt. And we did it. And earlier this year, we shared this publicly for the first time. So here it is. Thermoplastic seaweed, or as we like to call it, TPC. This is a patented seaweed-based home compostable pellet that melts and flows wherever plastic goes. And we can use it for all different types of plastics, but we're starting with flexible films like I was talking about before. This is a durable, lightweight, moisture-resistant, super versatile, and almost luxurious product we call TPC Flex. And this represents the first time that seaweed can actually replace bags and wrappers and pouches at scale. And then we went a little bit above and beyond. We designed another technology, and we call it First Wave. This is a super, super rapidly degradable film. It can disappear within 4 weeks. It's totally translucent. And it's a great use case in windows and sachets. The response to these technologies has been incredible. Much like at Aspen, people are hungry for solutions. They want this to be the reality. We've received incredible feedback from brands, manufacturers, people in the plastic industry, people in the circularity community, ocean researchers, nonprofits, celebrities, and last year, Tom Ford even gave us the thumbs up. We won first place in the Tom Ford Plastic Innovation Prize, which is powered by Lonely Whale and teed up some incredible partnerships for us, including working with J.Crew to replace their poly bags. We're already testing these in their distribution centers. You'll get to touch this later. We're using seaweed to replace the sleeves that protect Burton's snowboards. Pretty cool. We work with a packaging distributor called EcoEnclosed to offer stock seaweed packaging. So any of you today, any one of us can order Sway packaging off the internet. We're using our First Wave film as a window. This provides a totally bio-based solution. The packages are customizable, so we've been doing custom runs like this seaweed windowed swim trunk package for the Miami-based swimwear brand Le Club. And then we can also customize the color of the film. So we're working with this footwear brand called Alice Gray to replace their poly bags using this beautiful blue color. And just this week, literally yesterday, the news came out. We debuted this partnership with John Florence, who is a 2-time world champion surfer, Olympic athlete, and we're packaging his swim trunks ahead of the US Olympics. Or sorry, the World Olympics. So now these materials are on the market. Home compostable seaweed-based materials are accessible in the real world across fashion, home goods, personal care, grocery. The performance has been vetted. Brands say they want it. What makes this idea truly futuristic, though, is that it's not just about replacing plastic. It's about creating benefit across the entire supply chain from sea to soil. So let's talk about that. We source seaweed from the ocean, and the material we have created goes to the soil. How can we regenerate both of these generous sources of life on Earth? Well, let's start with the sea. How many people here, show of hands, are already very familiar with seaweed? This is like my kind of room. We're in the right place. So for those who are less familiar with seaweed, you can imagine why it might make a good replacement for plastic. If you're walking down the beach, you pick it up, it's stretchy. That's because it's spent millennia swaying in response to the rhythm of the ocean. It has natural polymers inside of it, agar, alginate, carrageenan, that are already industrially used across industries as thickening agents. So we can use those natural polymers that are already inside of seaweed to replace plastics. But we also chose seaweed because it's abundant. It grows on every coastline in the world. 35.8 million metric tons of seaweed are cultivated every single year, and that number doubles every decade. And then it's also really low impact. So it doesn't need arable land, fresh water, pesticides. It grows very fast. Some strains of seaweed grow up to 2 feet a day. They're like the bamboo of the sea. And then it's doing a lot of good on top of that. That's not all, you know. Seaweed provides nearly half of Earth's oxygen. It provides food for nearly 4 billion people. It provides habitat for literally millions of species. And it sequesters naturally 173 million metric tons of carbon every year. So our theory is, by working with a vetted network of ocean farms, we can help ensure the balance of ecosystems and communities and extend those positive benefits with scale. And we're increasingly working with a variety of different types of seaweed, including sargassum that's washing ashore on the Caribbean, helping to alleviate some of these pressures. Really, the theory is, done responsibly, we can help the oceans become even healthier. So that's the sea. Now let's go to the soil. Okay, again, show of hands, who here composts? Yeah, all right. So we love compost. Composting is an inevitability. We need to maintain the cycle of biological circularity. There's no justification for why any organic matter should be going into landfill. And to actually address the sheer volume of plastic that's being produced and mismanaged every single year, it's entirely possible that recycling will never meet that challenge. So while it's constantly improving, we need to also invest and expand in composting infrastructure and behavior. That's why sway materials are all designed to decompose rapidly, naturally, while lasting as long as they're needed. We've tried to create optionality. So home composting means the material can be mixed in with your food scraps. It can go in your backyard compost. You can put in your mill or your loamy, and it's going to disappear entirely in less than 6 months. It can also go in industrial compost, less than 48 days. And then in the event that the material falls out of the compostable loop, it's still going to be non-toxic and decompose certainly much faster than plastic. And there are added benefits to continuing to invest in compostable materials and infrastructure, and it empowers individual action. At a time when people really don't trust materials, home composting is the one end of life you can see happen right before your eyes. It also helps solve for non-recyclable plastics like meat trays and cling film and all kinds of bags and wrappers. And then it also supports soil as carbon sinks. More composting means more compost. More access to composting means we're investing in soil health, diverting food waste, reducing landfill emissions, and applying compost to soil everywhere can help in sequestering additional carbon. So, if any of these ideas are resonating with you, I invite you to join us on this journey. If you are working with a brand, we'd love to talk about your packaging system. If you work with a manufacturer or know a manufacturer who might be interested in participating in this new wave of materials, we are expanding. We have reached production scale. And if you're an individual who's motivated, I hope you have conversations with your kids, with your colleagues, with your loved ones, that there are real solutions for plastic that come from all sorts of sources that can actually do more and replenish this planet. Thank you so much for allowing me to share this inconceivable future, and please join us on our mission to sway the future.
Let's see. Thank you, Julia. Thank you, Harry. I want to start out by saying that I'm really honored and moved by following Harry and Julia, who are showing innovative solutions that, if we can figure out how to bring them to life, I think we know that we'd like to have them. What I'm going to talk to you about are things that we're not sure whether or not they're a good idea, but there are things that we're starting to look at because the climate system is in a dangerous place. So I'm going to talk to you about research, and I'm going to talk to you a lot about what we don't know and about what people are trying to learn. And I'm going to keep emphasizing that we don't know whether or not these things are a good idea. And so if you're here and you're worried and you think these might not be a good idea, we're right there with you. So, the reason that we're here in the category of things that I'm going to talk about is to do with trapped heat energy in the Earth system. So we know the cause is greenhouse gas emissions from human activity. We know we have to bring those emissions down, but we've got a really dangerous level of heat stress now in the Earth system. It's faster and bigger than scientists have been expecting. We're seeing impacts now that they didn't expect to see till the middle of the century or the end of the century. We've got people dying from surface heat. We've got massive flooding. We've got lots of impacts going on almost everywhere in the world. I was just reading this morning about wildfires in the Arctic region. And so the other thing that we have, which scientists are beginning to get very worried about, is that certain really important natural systems are starting to show signs of approaching dangerous tipping points that would fundamentally change the Earth system as we know it, and tipping points that might involve the release of greenhouse gases from natural systems at very large scales in a way that we wouldn't be able to manage. And so the question is, if we're starting to see signs of that, and if we're faced with that kind of risk, what options do we have? Because it's really important that we solve for safety. It's really important that we solve for safety of everybody here, everybody around the world, and the natural systems and ecosystems and animals, if you've been to the Zen room, that we care about. So what we can see is, the problem with this trapped heat energy is happening really fast. In Earth system terms, it's happening in a flash. And we've gone from, this sort of stable average over thousands of years to this very high pop in trapped heat energy. And one of the things that I learned, I came from the technology sector, so I'm not a scientist, but I worked with scientists now for about 15 years. I came into it with curiosity, probably like many of you, and I asked questions about what the nature of the risk was that we might be faced with very extreme runaway climate change. And one of the things that the scientists told me is that greenhouse gases stay in the climate system for a long time, 100 years or more. And so as you bring down emissions, you still have the greenhouse gases in the atmosphere, and you have some latent processes in the Earth system that mean that you get a residual warming. And what I'm showing you here is the UN IPCC charts. And in these charts, it almost looks like COVID curves, right? And in the charts, you can see that in every scenario for emissions, even the blue ones where we do really well, the Earth system continues to warm through about 2050. And it might be even going a little bit faster than this chart. So where we are today is not the end of the warming we're going to get, even if we do everything that Jane Fonda wants us to do. And so the question is, what do we do about that risk? And so the reason that I started my organization, Silver Lining, is because I was meeting scientists and other people who were starting to be aware of this risk and wanted to call it to people's attention and to say there are two things we need to do with regard to that risk. We need to understand it better. So we need to be able to better define the uncertainties that are associated with what will happen to the Earth system as it continues that little warming path that we're on. And then, is there anything that can bend the curve? Are there any things that could help improve the safety profile of this situation? And we would only want things that we could really understand would improve the safety profile of the situation. And so the comparison I would make are vaccines. So you need to do the research on vaccines, and you need to know that they're safe and effective. But if they are, then you might be able to bend the curve. And so when I asked scientists what our best candidates were for bending that curve, what they talked about is one of the ways that the Earth system regulates temperature, and it's the reflection of sunlight from clouds and particles in the atmosphere. It's why the Earth looks like a shiny dot from space. And because of things that they've seen in relatively recent history, they believe that if you increase this reflectivity by just 1 or 2%, you could offset 2 degrees or more of warming. And so in doing that, you might be able to extend the amount of time that the Earth system is stable, that impacts are lower, while you're reducing emissions. And the reason that they think that, and the reason that they think they have evidence for that, is because they've seen it in a couple of different ways. And one of the ways is a form of this kind of effect that's happening now, produced by anthropogenic pollution. And the picture that you're seeing here is a bank of clouds off the Pacific West Coast, and the bright streaks in the clouds are made by the emissions from ships. And so it turns out with pollution, you have not only greenhouse gases that mix with the atmosphere and stay for a long time, you often have particulates. And the particulates do two things. They can form a haze, like you see in LA smog, or they can mix with clouds in ways that make them brighter, like these bright streaks here. Those particulates are short-lived. They only last for a few days or a week. But when they have that effect, they're sending sunlight back into space, kind of like a white parasol. And so one of the things about this white parasol effect is that our pollution is producing it now. And that's pollution from ships, like you saw in those ship tracks, but also pollution from Chinese coal plants, from automotive emissions. Anything with particulate pollution that's wafting up into the low atmosphere could produce an effect that is countering some of the warming we would otherwise experience. This is another IPCC chart from the UN. And this is a chart that represents the effects on the climate system of human pollution. The pink bars are the warming effects, which you're familiar with from greenhouse gases and other things. The blue bars are the cooling effects from these particulates, which scientists call aerosols. And so you can see the shorter bar is that direct haze effect, and the biggest bar is the effect when the particles mix with clouds and make them brighter. But what's really notable about this chart, and I'm sorry it's not easier to see, are those little white spider lines which represent uncertainty. So the most uncertain thing about what's happening to the climate system in warming and cooling is the effect of those particles on clouds. It's the biggest thing that we don't know. It's the biggest portion of that total uncertainty bar. So one of the challenges that we have is one of the things that we're doing really well as a society is cleaning up that particulate pollution. And you may have seen news stories about this recently because the International Maritime Organization implemented regulations to clean up shipping emissions over the past couple of years, and they did it so well that you actually don't see as many of those ship tracks from space in the satellite pictures as you did before. And what happened was that coincided with record warming and record ocean surface warming last year. And so scientists right now are trying to study, how much of that might be associated with the loss of that pollution cooling effect. And the other thing that scientists are trying to study is whether there might be cleaner, safer ways to produce the same effect. And in the early 90s, a couple of British scientists postulated that maybe you could use sea salt particles from ocean water to brighten clouds over the ocean to produce a similar kind of effect in a cleaner, a more controlled way. And today, that's one of the things that scientists are interested in studying. And it turns out that the research on this effect is very likely to help us better understand what will happen if we reduce those pollution aerosols, those pollution particles. So it's a very kind of dual-purpose type of research that scientists want to do. So I'm going to come back to what that research looks like, but I also want to talk to you about the other form of this kind of atmospheric cooling that scientists have looked at, the most prominent form, the scariest form, which is putting particles in the outer layer of the atmosphere, or the stratosphere. And one of the reasons that scientists think that this might be helpful is because it's happened before in the recent past. And when Mount Pinatubo erupted in 1991, it was such a big volcano that it pushed particles all the way up to the stratosphere in large quantities. They stayed in the stratosphere, and they circulated and they cooled the planet for over 0.5 degrees centigrade for almost 2 years as the effect receded. So I can see that many of you in this room are like me. We were alive in 1991, and we've experienced this effect. And we've experienced planet cooling because of this effect. And one of the things that scientists saw after this was a change in the Arctic ice record. So when Mount Pinatubo erupted, the Arctic ice was receding. It was on a trajectory to recede. After the eruption, that gray bar that you see, there was a pop back of the Arctic ice from the cooling that was produced. And so scientists asked the same question, well, is there a cleaner, more controlled way that you could produce the same effect? And could you produce that over enough period of time, maybe to help us as we're trying to transition away from greenhouse gases into other things and keep the system stable? And so that idea of brightening the stratosphere with particles, sometimes called stratospheric aerosol injection, sometimes called geoengineering. We, in my organization, in my circles, we don't talk too much about geoengineering because unlike the work that Harry's doing, we don't see it primarily as an engineering problem. It's a really important science problem. We have a problem of safety and efficacy just like we have in medicine. We have to do the science. We have to do it in an open way. We have to do it in a shared way with the rest of the world. And we have to be very candid about what the realities of these things are and their risks. And they do have risks, as you might imagine. Putting particles in the stratosphere, one of the risks people are worried about, of course, is the ozone layer. What might that do to the ozone layer? I'll come back to that risk of the ozone layer, but the object of study and the thing that scientists really want to be able to do is to project forward what would the world look like under warming? What would it look like with these different forms of intervention? And can we understand the side effects and risks of that and compare it to the side effects and risks of warming? And we want to do the thing that makes us safer. This is a simulation that my colleagues were the first ones to do of a more realistic climate model simulation of putting material in the stratosphere against a business as usual case for warming, which is hopefully not what we're doing. But what you can see in that simulation is that, most of the world is a lot safer if that's the trajectory that we're on. The issue that we have today is we have a lot of work to do to be able to really do that simulation and really understand these things well. And if we don't understand these things well, there's a chance that people might try to do them anyway, and we won't understand these things well. We also don't today have the things that we need to monitor, regulate, and govern them. So it's an important thing from our perspective to say, what do we need to know? What do we need to do? And one of the things we've done over the past 5 years of my organization's life is work with scientists and science policymakers to say, what is the sort of collection of things that we as a society should try to look at if we were serious about understanding these things and helping the world be able to monitor, regulate, and make decisions about them. We published a report which describes a path to scientific assessment that would be an international assessment that was enabled by especially things that we have and know how to do in the United States. So you can look at that, but I'm going to talk about some of those things. One of the things we need to do is improve our climate model projections. And I'll say this, I'm not a scientist, you'll hear from scientists, but one of the biggest weaknesses in climate models is the representation of the impact of particles on clouds and how that affects climate, that uncertainty bar that I showed you before. So there's some work that we need to do in the climate models pretty quickly that's general and that's important to these problems. There's some gaps that we have in the kinds of observations that we need to see these aerosol particles in the atmosphere. So if we think that people might start to think about putting particles in the stratosphere to cool the planet, because that's one of the top candidate approaches, one of the things we need is the observations to see them. This is a WB-57. It's a NASA aircraft. It's one of only 4 research aircraft in the world that's fitted to fly in the stratosphere for research. And these planes had not been sampling the stratosphere since the 90s, until a few years ago when they started again and took a couple of sampling runs into the stratosphere. And they found that there was new aerosol pollution in the stratosphere. They used highly specialized instruments, which again are special to the US because they have these aircraft. And what they found was there was pollution in the stratosphere from space traffic. And the pollution from the space traffic is the same SO2 material that the volcanoes put in to cool the planet, that some people are thinking about to put in the stratosphere to cool the planet, that we don't know enough about. So we have a gap now. Those planes right now are only funded to fly every other year, and they're on soft money. They're quite vulnerable. There is one satellite that is equipped to observe the stratosphere. It's scheduled to go offline early next year. So my message about this, and we do some work as well with gaps in observations in the low atmosphere, where the weakest environment is the marine environment where the ships fly. And then we do some work with the kinds of active R&D studies you would need to look at the cleaner, safer particles and what they might look like. And that right now today exists of doing lab work and the ability to generate particle streams that you could go and study at very small scales to populate those models that would tell you what would happen if these things were used at larger scales. This is really important because none of the scientists that I work with advocate for doing anything that would have an impact on the environment, but they think it's really important to study these aerosols as they might be used in very small scales to populate models that would tell you what would happen. So they had hoped to do this in California and still do. And they hope to do this in environments that are very open, where people can come and see and other scientists can come and observe what they do. In this case, this experiment was the size of the deck of an aircraft carrier ship to study the evolution of particles, to populate models, and then to have those models of that localized area feed into the models of the regional area and of the planet. And so I'll finish off by talking about, what is the state of play of this research overall? Because on the one hand, it sounds very science fiction, very scary, very concerning. On the other hand, it's moving into serious places. So the United States government has initiated basic science research related to aerosol particles and their behavior in the atmosphere, both pollution and these active interventions. They published a report, an interagency report with 10 science agencies about the research required on these topics last year. In the UK and Europe, they've also published reports, and in the UK, they've launched research programs, both a technical research program and a modeling research program. And I'm missing the slide about the United Nations. Is it there? Sorry. This slide is supposed to have 3 reports from the United Nations. So if you visit our website or you contact me, I will tell you what they are. But one is from the United Nations Environment Program. One is from UNESCO, the World Heritage Program, which also has a lot of indigenous programs within it. And one is from the Montreal Protocol Scientific Assessment Panel, which looks after the ozone layer. All 3 of those reports recommended research in this area, and they recommended international scientific cooperation. So what we're seeing today is that, you know, the state of the climate system is such that these official bodies are saying, you know, this is an important area for the world to understand. It's also important because there are always people who are interested in looking at the commercial opportunities of these things. And you may have heard there's already been a company that's launched a potential approach to selling credits for cooling the planet based on releasing small amounts of pollution into the air. And we worked with some scientists to sort of debunk that idea. But you know, these ideas can catch fire pretty quickly. People get very excited about whether there are scaled solutions for dealing with climate change. And one of the ways we counter that kind of thing happening is with research and with data. So we think that's going to be really important, and we think it's going to be really important that there's philanthropic support for research, that there's government public research, and that there's coordinated international cooperation on research in these areas. And so we started a little bit down that path, but what we don't know is pretty staggering. And so we also think it's a bit of a matter of urgency now. And one of the reasons we think that is because of the risk. So I'm going to finish off by talking about disaster risk. For those of you who don't know, we have a planetary defense office in NASA, and we have a program for managing the risk of very large asteroids striking the planet, which is about a 1 in 50,000 odds between now and the mid-century. And that program is active at $200 million a year, and there are now laser platforms in space for shooting at asteroids. Another macro level risk that the government has looked at is the Yellowstone supervolcano. If it erupts, that would be catastrophic at a planetary level, certainly a US level. They've had a workshop on that, and they've made recommendations about how to mitigate it. It's not funded, but that risk is about twice as big as the asteroid risk, at about 1 in 25,000 in the next 30 or 40 years. And then we have tipping point risks. And the collective tipping point risks that we're facing are, conservatively described at 10% or higher in the next few decades. And we don't have a disaster risk program for that. So our call is, can we do the research? Can we think about this in terms of disaster risk? Can we know that we're not going to try to market and sell this? We're not going to try to pull the wool over anyone's eyes. But if there's any way that these things could make us safer in the context of the risk profile that we're facing, let's do the work, and let's do it with the scientists who want to do it openly. Thank you very much.